through this here, y'all kind of got the hang of it, or if you already got a good understanding of it, it kind of cleared a few things up and then we were good. So, and that's really what we'll do. So we'll definitely look at the first 3 and then probably 2 more after that. So we're looking at 5 to 6 problems and then we're actually done for today. Now, the first one we're looking at is this one here. The 6 over 3x minus 1 is equal to 3 over 4. Now, the textbook here for these problems talked about using cross multiplication. And you've probably seen this before where we cross it and multiply. I don't like this method. It's not that it doesn't work. It works just fine for this here. But once we get more than one fraction on either side of the equation, it doesn't work anymore. And I don't see the point in doing and going over a method that only works if it's set up exactly like this here. And then once we hit a different type, well, we got to go over a different way to do it. And essentially, the way that we go through and solve these, and we're going to solve this one here, is exactly the same thing as cross multiplication, but we're not using a fancy little trick to be able to do it. So, now when we look at any of these here, it is always good to find the restrictions first. Because if we find the restrictions, and once we finish solving it and one of the numbers comes up as a restriction, we don't have to plug it back into the equation to make sure it works, or it doesn't work. And for this here, the only place that there is a chance of having a denominator being 0 is at the 3x minus 1. Because if 3x minus 1 is 0, then we have 0 in the denominator. And to find it, really, we just set it equal to 0 and solve. So here we would add 1 to both sides. And so telling us that 3x is equal to 1. Divide both sides by 3, telling us x is equal to 1/3. So if x is equal to 1/3, it gives us one of our restrictions. And we won't be able to actually plug it back in. It doesn't work in the original equation. So we do this here just to find the restriction. Now we can go on and actually solve. And when we solve these here, any of the ones we do today, we want to see what can we multiply every single term by so that the denominators simplify out. Well, one of the things we can multiply both sides by is by 4. Because on the right-hand side, the 4 would simplify out in the 4 in the denominator. What else would we need? The 3x minus 1. And if we multiply both sides by 4 times 3x minus 1, on the left-hand side, the 3x minus 1 and 3x minus 1 would simplify out. On the right-hand side, the 4 and 4 would simplify out. And it would leave us with 6 times 4 is equal to 3 times 3x minus 1. And well, and now we can go on and start solving. Now, for those of you who do remember cross multiplication, it is where we multiply these two and set it equal to the multiplication of these two. Well, once we finish simplifying, what did we get? That exact same thing, yes? So the reason that cross multiplication works is essentially we're multiplying both sides by the least common denominator, what we just did, and it just simplified out. But this here makes a little more sense, yes? Than just we cross and multiply and it works. Now, I've also said this to all 3 classes, like the 6 times 4. We don't have to write it as 6 times 4. As we know here, well, 6 times 4 is 24. So if it's something that you feel comfortable with, like I've been saying the last few days, go on and multiply it. We don't have to rewrite it back out. And if we feel comfortable with doing the 3x times 3 is 9x, and 3 times -1 is -3, I really could have gone from here to here and just done the multiplication. I didn't necessarily have to rewrite it. If that's a lot to do and you don't feel comfortable doing it, go on and write it out. But there is nothing wrong with seeing, okay, this is 6 times 4 gives me 24. This is 3 times our 3x minus 1 will give us 9x minus 3. There's nothing wrong with jumping to there. But we just need to make sure that we are keeping the signs correct and distributing everything properly. Well, now we just need to solve for the value of x. And what can we do first? We can add 3 to both sides. And if we add 3 to both sides, well, 24 plus 3 is 27, which is equal to 9x. And from here we can divide both sides by 9, telling us that x is equal to 3. And that's our answer. Now we do need to make sure it's not one of the restrictions. And well, our only restriction was 1/3. 3 is definitely not 1/3. So that's the answer. That's all we have to do for this here. Any questions on any of these here? All right, let's go and look at the next one. We have 5 over x is equal to 7 over x minus 4. So it's good to start off with our restrictions. So what values of x do we know will cause denominators to be 0? 4 and 0. Because we can kind of see that by setting them up, because the one spot where we have x in the denominator is when it's by itself. So we set it equal to 0 and solve. Well, it's solved. So here, this is telling us x cannot equal 0. Our x minus 4 is equal to 0. Well, plus 4, so x cannot equal 4. So 0 and 4, if they come up as solutions, they would be considered extraneous solutions. All right. So what do we need to do first to solve this? We can multiply both sides by and x minus 4. And when we multiply both sides by x and x minus 4, in the first one here, the x and x will cancel out. Here, the x minus 4 and x minus 4 will cancel out. And let's see what we have left. In the first one, we have 5 times our x minus 4. And we could rewrite that as 5 times x minus 4. But if we feel comfortable, well, 5 times x is what? 5x. 5 times -4 is equal to 7 times x, which is 7x. Because if we feel comfortable doing that, we can jump straight there. We don't have to rewrite it as 5 times x minus 4 is equal to 7x. Because if we feel comfortable doing that multiplication, go on and do it. Any questions on this so far? Well, at this point here, we can do what? Minus 5x from both sides. So we get that -20 is equal to 2x. And last but not least, divide both sides by 2, and we get x is equal to -10. Was that one of our restrictions? Well, no. So that's a solution there. We'll do one more of these type, because I feel like at this point y'all are getting the hang of this, and they're actually becoming a lot easier than they were when we went over them the first time, yes? Okay. Always good to start with restrictions because, I mean, none of the ones here we're going to actually have a restriction come up, but they're still good to look for, just in case they do. And on the test, you might want to read the instruction because it might say in bold, extraneous solutions, kind of red flag, trying to help you out. But here, what would the extraneous solutions be? -1 and -7, because x plus 1 would be -1, because -1 plus 1 is 0. And for x plus 7, it would be -7, because -7 plus 7 is, well, 0. So those would be our restrictions. And what are we going to multiply both sides, everything by? 1 and x plus 1 and x plus 7. And when we multiply, well, here the x plus 1 and x plus 1 will simplify out. Here the x plus 7 and x plus 7 will simplify. Now for the first one here, we have x plus 3 times x plus 7. If you do feel comfortable going on and multiplying that out, you can do that. But if you don't feel comfortable doing that all in one step, that's fine. Because you can write it as x plus 3 times x plus 7. And we could write out the other side as 15 times x plus 1. Now, if you do feel comfortable with the left side, the x plus 3 times x plus 7, going on and stating that it's x squared plus 10x plus 21, that's fine. Or if you wanted to just multiply it out, like we're going to do here, x times x would give us squared. X times 7 is going to give us plus 7x. 3 times x would be plus 21, and going on and writing it out here, that works too. And this here is equal to 15x plus 15. And we multiply through by the 15. Now at this point here, we can combine like terms, which tells us that we have x squared plus 10x plus 21 is equal to well, since we do have a quadratic, we need to get everything on the same side of the equal sign. Well, we can subtract 15x from both sides, which tells us that we have x squared plus 5x plus 21 is equal to 15. Okay. Now at this point here, we can subtract 15 from both sides. Okay, yes. Because that shouldn't be plus, that should be minus. I knew something was supposed to be a subtraction, and I couldn't figure it out. I did that the wrong way. For some reason, I did 10 minus 15 instead of 15 minus 10. A little bit different. Last but not least, we need to subtract 15 from both sides to get this equal to 0. Is whenever we have a quadratic or a higher degree polynomial function, so whenever we have a variable with an exponent 2 or greater, we're going to need to get it equal to 0. Now we need to solve this here, yes? One of the ways we haven't really been using, we've used it a few times, is the quadratic formula. And I feel like for the most part, y'all, unless we absolutely have to use it, y'all are kind of shying away from it. It's not that it's bad, it's just a little bit tedious. And the main way we've been doing is by factoring. But there is one other method that we've kind of forgotten about a little bit, which is our graphing it. Because most of the time, if it is factorable, it is actually graphable. So here we can actually say x squared minus 5x plus 6 and hit graph. Okay, it intersects the x-axis at 2 points. We can look at the table, and again, we're trying to find out what value of x will make the y value be 0, and it does give us 2. Gives us one at 2 and one at 3. So what that tells us is that the solution for this here is that x is equal to 2 and x is equal to 3. That's it. And realistically, if we wanted to factor it, well, I have a feeling that this would actually end up being x minus 2 times x minus 3 are going to be the factors if we were going to factor this out. And if two things multiply together to equal 0, well, one of them has to be 0. In both cases here, so here we would add 2 to both sides. Here we're going to add 3, telling us x is equal to 2, and here x is equal to 3. Which is exactly what we got by factoring it. And I wouldn't advise doing that, working two equations at the same time. It's very easy to misplace numbers. And I will, if I do that, I will mix up numbers easily. I've already done it once today. So, but that is the exact same way as if we factored it or if we graphed it. It gives us the same thing. Now, I will say when we graph it, if there's a number in front of x squared and it's a quadratic like this here, then it's going to be a high probability of there being fractional answers. Because if there's a number there, it means that there's going to be a number, I keep erasing, here or here, which means when we solve, we're going to have to divide by said number, which means we're going to get fractions. So if there's a number in front of x squared, there's a high likelihood there's going to be fractions. Any questions on any of this here? We feel kind of comfortable with these here. Yeah. So we'll move on to the next type. Something like this here. Now I've talked to last hour, so fourth hour, not fifth. Fourth hour about some of these here, and I know some of these do show up on the ACT. Possibly. You've seen at least probably one or two, not a whole lot like this, but they do show up. And luckily with the ACT, unlike my test, they actually give you answer choices, yes, for solving. So if we look at it and all of them are whole numbers, we could actually graph this thing. We could actually plug this into the graphing calculator and it would actually do it for us. I would just get the thing equal to 0. Even though it has y instead of x, I could call it x and x and graph the thing and actually get the answers. And that would be an even faster way to do it than actually doing this by hand. So we are able to graph these to see if they work. Or if it's on the ACT and they give us answer choices, we can plug the answers in to see which values of y actually make this thing equal 1. And we could get it done. So on the ACT, especially where time is important, a graphing calculator does save time. Here, what do we know y can't be? 4 and 3. So if this was an ACT and there's answers of 4 and 3 down, we know immediately those aren't right because they're a part of our restriction. Okay. Now let's actually start solving. So what do we need to multiply each term by? y minus 4 and y minus 3. Now looking at all these here, the first one, our y minus 4 and y minus 4 would cancel. In the middle, the y minus 3 and y minus 3 would cancel. And well, since it's equal to 1, it doesn't have a denominator, so nothing would simplify there. And on some of these here, we've been going through and I've been saying like we could go on and multiply. We don't have to rewrite it out. This one here, we need to be careful. Because it's very tempting to bring this down for the middle term and say negative 3y, because 3 times y would be negative 3. And then saying 3 times our negative 4 would be negative 12. But this isn't right. This would not be the correct expression. I'm going to erase it. I don't like having it up there. Because when we do this here, we do have 4 times y minus 3. And then we have what? Negative 3 times y minus 4 is equal to our y minus 4 times y minus 3. Because what are we actually multiplying the y minus 3 by? Or y minus 4 by? Not just 3, but negative 3. So when we do that multiplication in the center, oh here, let's do it first. 4 times y would be 4y. 4 times negative 3 would be negative 12. Here, negative 3 times y would be the negative 3y, which we would get because we would bring the sign down from the subtraction and the 3y. But we're actually multiplying the negative 4, not by 3, but negative 3, which would give us a positive 12. So that's one thing especially to be careful of is with those signs. Because with all the ones we've done so far, it's either been plus or positive, so it doesn't matter. To make sure we're having to check the signs, because they won't change. Here, we have to be careful with it. And on the other side, we can go on and use our distributive property, which would tell us that we have y squared minus 3y minus 4y plus 12. Any questions on any of this here so far? Well, the left-hand side of this equation is actually kind of nice. 4y minus 3y is, well, it would just be y. Negative 12 plus 12 is 0. Okay. So the entire left-hand side simplified to y. The right-hand side, we're going to have y squared. I'm going to try to write y squared. Negative 3y minus 4y would be negative 7y plus 12. And last but not least, we would subtract y from both sides, telling us that we have 0 is equal to y squared minus 8y plus 12. Any questions on this here? Now the solutions that we're looking for, because there's not a number in front of y. So in our factorization here, if we're thinking about this, well, we're just going to have y and y for that first term, yes? And the other term is just going to be the factors of 12. So really the only solutions that we can have are 1 and 12 or 2 and 6 when it works out. Since that's plus, we'd have minus and minus, and it works out to be 2 and 6. Now, if you're able to factor, especially, and this is referencing back to the ACT or even this test, you get down to this here, y squared minus 8y plus 12. If you're able to factor this faster than you can graph it in the graphing calculator, go on and factor it. If you can graph it faster, go on and graph it. Yes. Well, we have two things multiplied together to equal 0, so one of them must be 0. So either y minus 2 is equal to 0 or y minus 6 is equal to 0. I do find this kind of interesting because here we would add 2, and not interesting of what we're actually doing here. So we get y is equal to 2. Here we would add 6, telling us y is equal to 6. I find it interesting because once we got to the y minus 2, y minus 6, is solving for those any different than what we did at the beginning for solving for our restrictions? No, but I won't. But we didn't have to actually walk through that, but I walked y'all through this. Same exact process, but I found that interesting. I think it was third hour. It dawned on me, but we get these two here. And neither one of those is the restriction, so both of those answers work. Any questions on this here? Well, why don't I show you all this? Alpha y equals, enter. Let's see here, so I can clear the whole thing out. Y equals, enter. I'm going to borrow your notes for a second, Michelle. I'll give them right back. Because the one we just worked was 4 over. Now, in the problem it said y minus 4. But switching it from y to x isn't making that big of a difference. And it was equal to 1, but I got it equal to 0 because I moved everything to the same side, because realistically, we're trying to see what's going to make the two sides be the same. Or if I subtract the 1 from both sides, it's trying to see what's going to make it equal 0. And we can graph it. And it gives us this here. It is a funky looking graph, but again, we're still trying to see what value of x is going to make this function equal 0, just like with the quadratics. Second graph. So we're trying to see where y is 0. 2 is 1, and it gave us the solutions. So that's not too bad. If the solutions are fractional, we might have to do a little more work to get to it, but the graphing calculator will do these for us, especially if we're solving. Any other questions on this here? This is the last one we're going to look at. Now, before we jump into finding restrictions, because that's normally what we do first, I want to find what we're going to multiply each of these terms by. What would we multiply each one by? Well, we know we need an x, yes? So we're going to use x. We'd also use x plus 1. Would we use anything else? And again, there's a reason I'm leading into it this way, because it'd be very tempting to also say x squared plus x, taking each of the denominators and multiplying them through. But the middle one does have a greatest common factor between those two terms, yes? It has an x. Now, if we factor that x out, because the rest of them don't need any simplifications in the denominator, but if I factor an x out of x squared plus x, I get x times x plus 1. So would I have actually needed to multiply through by the x squared plus x? No. All we would need is the x times x plus 1. So in solving these here, if any of the denominators we can simplify them, either by factoring out a greatest common factor or our two sets of parentheses, or factoring in any way, shape, or form, it's good to do that first. Because if we'd have multiplied with this here, it would have increased the degree by 2. Because for each extra factor we multiply everything by, it will increase the degree by 1 for variables. And if it's just a constant term, it's just going to increase it by that scale. So if we put in an extra 2 where we multiplied, everything would have been increased by a factor of 2. Now numbers, if it's 2, 4, 6, 8, isn't difficult. It just makes the numbers look bigger. Variables, on the other hand, take it for if this is a linear, something like this here, and I add 2 factors in, because now it's going to be a cubic. We're having to deal with degree 3, which can make them harder to solve, on top of the fact that the values or answers that we add are the restrictions. And here the restrictions would be 0 and -1. So for each one of those that we add in, if we add an extra x, well, the solutions would be whatever we're supposed to get, and then 0. Well, we know that 0 won't work. Or if we add an extra x plus 1, we would actually get a solution of -1. Well, neither one of those work. And here, we just need x and x plus 1. If you're not sure that you need something extra, go on and start with what you know for sure and cancel out and see what we have. In the first one, the x plus 1 and x plus 1 would cancel out. In the middle, the x times x plus 1 would cancel out with the x times x plus 1. And if I look at the last one here, the x and x would cancel because they're like on top and bottom. Do I have anything left in the denominator? Well, no, so I got the correct thing to multiply. If there is something left over, well, I can go on and add it in to the multiplication and then simplify it out. Because it's easier to add to it than to try to pull something back. Now let's see what we have left. On the first one here, we have 2 times x, which is 2x. Minus 1 is equal to 3 times x is 3x plus 3 if we multiplied it out. That's actually not that bad. Well, now we just need to solve for the value of x by subtracting 2x from both sides. These cancel. I'm apparently just going to straight up erase it. Which tells us that -1 is equal to x plus 3. And then what can we do? Subtract 3 from both sides. Which tells us x is equal to -4. And that's it. That's all we have to do for these here. Any questions on this here? So if we'd actually multiplied this through by our x squared minus x, we would have still gotten x is equal to -4. But we would have also been told that x is equal to -1 and 0. But what do we know about -1 and 0? They are our restrictions. So we would have ended up crossing those solutions back out. And this would have also been a lot nastier problem to work with. Because what we would end up having is 2x times x squared plus x minus x times x plus 1 is equal to 3x times, we wouldn't have the x, yes, this here. That's what we would have to actually start simplifying if we included that extra one in. Y'all would agree that's taking it up to another whole level of difficulty. And this actually shouldn't then, yeah, that's correct. And that's all because we included just that extra factor of x squared plus x. So, but are there any other questions on any of this here? If not, that's it. The last assignment for Chapter 7 is a worksheet. And then we are done.